problem that we are trying to solve is a very real problem, okay? So I can assure you, all of you actually have encountered this problem. So this is simulation of an internal combustion engine. So the car that you're driving, whether it's GM, Chrysler, Ford, Toyota, Nissan, or Kia, or whatever it is, it actually has an internal combustion engine. So I'm going to talk about how we are trying to improve the scalability, how we are trying to improve the performance of an internal combustion engine by doing some simulations. So before I start, I'd like to acknowledge some people. So 70% of my funding is from DOE. So of course, I need to acknowledge my program sponsors. We have a lot of collaborations with the industry. It's very difficult to get money from the industry, and when they give some money, they expect a lot out of you, but it's very rewarding when you are actually able to deliver to the industry. We work very closely with the ALCF and MCS. I have a couple of names that are listed there who have helped us a lot: Dr. Marta Garcia, Kevin Harms, and Joe Ensley. Joe Ensley has been helping us with a lot of these visualizations. Kevin Harms and Marta have been doing a lot of the scaling studies and performance improvements for us. We are mechanical engineers, so we are learning computer science, so it helps to have collaboration with ALCF. And we also work a lot with the chemistry group. The reason we work with the chemistry group is fuels. So if you're changing a fuel, the fuel chemistry changes. That needs to become part of our simulations. So of course, we try to work with the chemistry folks. Before I start, I wanted to show you this slide so that everyone appreciates that we are still going to burn renewable fuels in 2030, maybe even in 2050. So when I was growing up in the 80s, everyone was telling me, oh, by 2010, we won't be burning coal. We won't be burning fuels. We will be running electric cars. It's 2010. It's 2015. We are still running. We are still burning fuels, and the reason is because we are finding new sources of energy, right? So we are finding new sources of energy. We are finding new sources of coal, natural gas, and oil. So that's great, right? We find new sources of energy, but as a community, our responsibility is to burn them more efficiently, okay? So just the fact that we are finding more resources doesn't mean we just burn them like we do, right? So that's basically the role of my team, and that's basically the role of DOE, to burn these fuels more efficiently and to make US more independent. So the area that I work in is internal combustion engines. This is just a movie that Joe Ensley from ALCF generated. This is basically showing what we are trying to simulate here. This is actually a GM 1.9 liter diesel engine. It's a 4-cylinder engine. We are simulating one of these cylinders. Janardhan actually performed this simulation. And what you're looking at here is a fuel that's being injected at the top. It's a 7-hole injector. And the fuel, as it comes out, it breaks up into smaller droplets, and then it evaporates. Then ignition happens, combustion happens. That basically results in the power stroke that basically drives your vehicle, right? So this process is actually very challenging. It looks very simple when you do an animation, but the process is very challenging because the nozzle diameter is 100 microns. That's really small. That's about the diameter of your hair. And the engine RPM is 1500, 1600 RPM, revolutions per minute. So you can appreciate the length scale and the time scale that we need to resolve in order to do this problem correctly, right? So that's some of the challenges that I've listed here. The problem with this case is that there is also two-phase flow physics. So anything complicated you can imagine, an engine will have it, okay? So this has two-phase flows. We need to resolve the flow inside the nozzle where cavitation occurs. No two cycles of an engine are the same. You can kind of feel it when you're driving. If you're driving in the highway and you have set cruise control to 65, I can assure you that no two cycles of your engine are the same, right? So how do we account for that in our simulations? Like I said earlier, combustion chemistry, fuels are changing. So the fuels that we burn in North America is very different from the fuel that we burn in Asia. Well, the fuel we burn in Illinois is different from the fuel we burn in Texas. So how do we account for those in our simulations? Of course, we have moving boundaries. Like I said, spatial convergence, grid convergence is a big challenge. And then getting the emissions right and soot modeling right is very difficult because you have to get all the processes upstream correct to actually predict the NOx and soot. And the OEMs basically want us to predict NOx and soot, and it's very challenging. And then, of course, the new things that we are getting into is conjugate heat transfer. So for example, for the longest time, we were doing simulations of diesel engine, spark ignition engine, and we kind of understood what are the temperatures that you expect, what are the peak temperatures, and we would design our materials based on this. But now we are moving into this area where we are doing low temperature combustion. So we are trying to intentionally keep the combustion temperatures low. So obviously the material requirements are not going to be that stringent. So how do we couple our understanding of the combustion and the fuels and what's happening near the boundaries to designing the materials? So these are all the challenging issues that we are facing. So the dream is, of course, to design an engine based on simulations, and that's of course a dream. I don't think anyone has realized it, but the true challenge is if you can actually design an engine faster than experiments. So all experimentalists would tell you is that they can actually design their engine pretty efficiently because they have been doing that for the last 50 years. And simulations only form a part of it. They only provide some insights, but engines have not been designed based on simulations. So that basically brings us to the reality. The reality is that engine simulations are quite simple, and I have a couple of slides talking about why they are simple, why the industry wants simple calculations. And the main reason is because our uncertainties are poorly understood. So we basically need some sort of a transformation function, which is basically the goal of my team, is to develop predictive computational capabilities, which would be aided by high-performance computing. So this is a slide that I borrowed from Dr. John Doerr. He's director of combustion at Cummins. And Cummins also has this vision that they want to co-optimize engine and fuels. We have a lot of collaborations with Cummins. And in general, when they say they want to co-optimize engines and fuels, John Doerr feels that these are the factors of speed up that are necessary. So for example, when in industry, when they do simulations, they do sector simulations. So they do not do the full 360. And of course, they miss some physics. So if you want to do the full 360, that's a factor of 10 that's required. Like I said earlier, no two cycles of an engine are the same. So if we simulate just a single cycle, of course, we are missing physics. So that's at least a factor of 10. More complicated models, industry tends to use what we call as RANs, so average, time averaged models. And of course, they do not work very well. So if you want to use some sort of LES model, that's a factor of 10. If you want to resolve the two-phase flow physics, that's easily a factor of 10. And then if you want to really understand the chemistry, so in general, when we represent a fuel, we tend to represent it using one or two components. That's very simplified. A real fuel consists of maybe 1,000 components. So if you want to add that complexity, that's easily a factor of 50. And we wrap around uncertainty quantification on top of it, this becomes a really expensive problem. So the industry wants to solve this problem within 24 hours. So they want to press the button tonight. When they come back tomorrow, on 64 processors, they want some sort of a solution. Whether it's right or not, that's the solution they want, right? So for us, but for us, what we are trying to do is if we multiply these speedups, and all these are multiplicative, this actually is an exascale problem. It's actually easily an exascale problem without any stretch of imagination, right? So I think we are pioneering some of this work in trying to scale our engine simulations on supercomputers like Mira, and I'll show you some of our results. So reality is that the existing resources, none of the existing resources are exascale. So, which is okay, but the more harsher reality is our engine codes don't even scale on 100 processors. So I have no reason to complain, okay? So this is what we are trying to do. So in general, engine simulations, in industry, in academia, also maybe 4 or 5 years back in national labs, it was safe to say that engine simulations were highly tuned. We wouldn't resolve the flow inside the nozzle. We would tend to use simplified models in terms of spray, in terms of combustion. And really load balancing was not an issue because we were running on 8 processors or maybe even 64 processors. Load balancing wasn't an issue. So the strength of this approach was when we matched experimental data after tuning, then the CFD could provide a lot of insights. And in the domain where it was validated, CFD was very helpful. And industry does that all the time, you know. They would get some experimental data, validate their CFD model, and then go from there. Now our approach, and we are calling this a transformational approach, is this way. So we are going to use detailed chemistry-based combustion models. we are going to use finer and finer meshes pushing towards grid convergence. When I started my postdoc at Argonne, I was surprised to find out that there was no grid convergent engine simulation done before my time. So that was quite shocking for me. So we have been able to do a few. I'll show you some. And then we'll be implementing better turbulence models. So we'll talk about dynamic structure LES model a little bit. Better two-phase flow model. So this is basically my background, doing two-phase flow simulation. So I'll focus a little bit more in these areas, looking at cavitation and things like that. And of course, to work with LES to make these simulations highly parallel, and so that we can move towards predictive engine simulations. So keep in mind, we are not there yet, and that's job security for me for the next 20, 30 years. Maybe job security for Janardhan also. All right, so let's get to the meat of the talk. So we actually use a commercial code. We use a commercial code Converge. It's used a lot by the industry, so we tend to use it. All our collaborative partners, Cummins, Caterpillar, GM, Chrysler, Ford, they actually want us to use this code because whatever model developments we do into the code, they can get it directly. So for example, if we develop something in OpenFOAM or Kiva, it's another additional step for them to implement that in their workflow. So the reason it works for us is because we have almost full source code access. So we have source code access to about 80 to 85% of the code. The 10 to 15% of the code that we do not see is basically their meshing algorithms. And that's their family jewels. They don't want to share with us. We are okay with that. But even with the 80 to 85% of the code that we have, we are able to do a lot of things. And I'll talk about it. We have actually done some of the largest engine simulations that are known. Some of the numbers are shown here. I'm not going to go into them in detail. The key thing I'll mention here is now we have shown good scalability on 4,000 processors. If you remember my earlier slide, in 2012, we were at 100 processors. So you can see the improvements that we have done. And these are some of the model improvements that we have done, implemented in Converge, and we continue to do that. Now the key thing also here is, for my promotion or for Janardhan's promotion, we need to publish. And working with Converge actually hasn't stopped us from publishing. All these models that we have developed are actually published, and you can go there and download all these results. So governing equations, I don't want to make anyone fall asleep, so I really simplified them, just mass, momentum, energy. This is a two-phase flow. So we basically have source terms for exchanging momentum, energy from the liquid phase to the gas phase. So the liquid phase is injected at say 600 meters per second. That's basically having your gas phase. The liquid phase is solved in a Lagrangian fashion, and the gas phase is basically solved in an Eulerian fashion. And these are some of the coupling terms that we need to account for. We have combustion, so we have species equations, and of course, based on what kind of closure you want for turbulence, we could use RANS or LES or whatever it is. We don't do DNS, that's really out of our box. So one thing I want to mention here is that adaptive meshing is a boon for engine simulations, because wherever we want to resolve the flow fields, we can actually put some mesh there. And you can see that this is a sector mesh that we are looking at. But really for our applications, what we have seen is for algorithms like Metis, we struggle with the load balancing. So this is an area that we are actively seeking some help, where we can actually improve the load balancing while using AMR. A couple of slides that I wanted to show in terms of results. So I have grouped my results in terms of capacity computing and capability computing. You guys have been in this workshop for last 1 week, so you understand exactly what I'm talking about. So when I say capability computing, I mean about 5,000 processors. In my field, that's really capability computing. And this work we have been doing in collaboration with Convergent Science and Caterpillar. We have run cases with about 50 million CFD cells. The other area of interest is, of course, to run capacity computing, and we have an ALCC award from ASCAR in order to do some of these calculations, where we are running, say, thousands of cases, still using maybe 5,000 or more processors. And the industry is really interested in these kind of problems where they can use optimization. So for example, we have done with some work with Fiat Chrysler, and then doing some uncertainty quantification, sensitivity analysis, LES realizations with Cummins. So I'll show you a couple of slides on these projects, basically to highlight the science aspects. So before I start on the science aspects, a couple of things about what we have done in terms of scaling. So this is some work from 2012 where we are trying to run an engine simulation on 256 processors. I know that's peanuts for you guys, but that's what we were trying in 2012. And these are some of the results. So the blue dots are results without METIS. So I'm plotting the cell count as number of cores, and this is at top dead center. So what we observe is without METIS, there were a lot of cores with 0 cells and a lot of cores with more than 8,000 cells. So the cores that had more than 8,000 cells absolutely ran out of memory, so our simulations would crash at top dead center. So working with ALCF and MCS, we implemented METIS, and this is the load balance. These are the red symbols that you can see. So you can still see that there is load imbalance, but at least there are no cores with 0 cells, and at least there are no cores with more than 6,000 cells. So we were able to proceed the calculation beyond top dead center, and these are some of the results. So without METIS, we were actually not able to do this calculation with about 34 million cells, and METIS allowed us to do this. And by doing this, we were able to actually run the first grid convergent engine simulations. And these are some of the results that we get. This is basically explaining why we observe grid convergence. It's because we are starting to resolve some of the relevant turbulence scales. I'll skip the details there. I'll talk more about the results here. So here I'm plotting cylinder pressure as a function of crank angle. Here I'm plotting the engine out NOx emission as a function of crank angle. And all these are plotted for different minimum mesh sizes. So I'm going from 2 millimeter minimum cell size all the way down to 100 micron minimum cell size. So if you look at a parameter like cylinder pressure, which is a global parameter, it's a cylinder average parameter. From our simulation, we observe that cylinder pressure basically grid converges at say 0.25 millimeter. So even putting more resolution really doesn't help you get better results or different results for cylinder pressure. However, if you look at a parameter like NOx, we see that it's highly non-monotonic. So NOx first increases, then it decreases. And unless we did a calculation with about 100 micron resolution, it was very difficult for us to understand where does NOx grid converge. Okay, so this was, again, in order to do this 100 micron calculation, we had to take about 14 days on 512 processors with about 50 million cells. And again, this wouldn't have been possible without METIS and without the HPC resources at Argonne. So continuing that work, then we ported the code onto Mira, and we started exploring this combustion concept called gasoline compression ignition. So it's a little bit tricky to understand. So typically spark engines or gasoline engines are spark ignited, and diesel engines are compression ignited. So here we are compression igniting gasoline fuel. So it's a mixture of two concepts, and what we are trying to do is to marry the best of both worlds. And it could be a disaster if it doesn't work, but the idea was to get the best of both worlds. And Janardhan actually performed a lot of optimizations working with our experimentalist, Dr. Steve Ciatti at Argonne, who is one of the pioneers of this low temperature combustion concept. And we were able to get some really nice results using Mira. And in order to get these results, we had to do a lot of code optimization. We worked with ALCF. These are some of the things that we did. I'm not going to get into the details, but I do want to highlight one new thing that we were, I think, quite new in the literature. I haven't seen this before. So for example, if you look at this cut plane, and here I'm plotting temperature, for example, if I look at processor P1 and P2, and if I just use METIS to load balance, it's quite possible that P1 and P2 have the same number of cells. However, the computational load on P1 and P2 is very different because the combustion chemistry is very different. The equivalence ratio is very different. So what we started doing, and this was in collaboration with Convergent Science, where we started actually load balancing the actual load. So we came up with a stiffness-based criteria, and we started load balancing the actual load. And this actually helped us quite a bit. So this is our scalability curve. This is speed up, number of processors. This is the linear speed up. And industry is somewhere here, 24, 48 processors, so they're way behind. But anyway, we start at 512 processors, and at 4,096 processors, we are about 80% efficiency. So in our world, that's pretty good. Couple of slides on the science aspects. So my background is nozzle flow simulations, spray simulations, two-phase flow modeling. So we work like ALCF is a resource. APS is also a resource at Argonne National Lab. APS stands for Advanced Photon Source. And with the Advanced Photon Source, we can make measurements like this. So we are actually looking at a fuel injector here. This is actually a single hole injector. The diameter of this injector is about 100 micron, again, the diameter of your hair. So those are the length scales we are trying to resolve. And if you look at this movie, there are a couple of interesting things. So this is actually governing the flow inside the nozzle. So when this is at this position, there is no fuel flow because the passages are blocked. The fuel flow begins when the needle moves up, but when the needle moves up and down, we see that it has an off-axis motion. It has a cantilever. It's basically a cantilever, so it has an off-axis motion. So in our simulations, we are actually able to mimic this, and this is our simulation result. And for a single hole injector, this off-axis motion was really not important. So then we showed this to GM, we showed this to Cummins, and they got very excited because their injectors are multi-hole. So a Cummins injector, production injector is 9 holes. So this is basically the needle off-axis motion on a Cummins 9-hole injector, hole 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see that looking at the top view, you can clearly see that the needle really wobbles a lot. There is a lot of off-axis motion. And then it's obvious to understand that because of this off-axis motion, there'll be a lot of plume-to-plume differences. And because of those plume-to-plume differences, the combustion will be different in every cycle. Okay? So based on some of the work that we did, this became basically part of the workflow in Cummins. And some of this work is basically going to feed into the 2025 engine design. So their 2019 engine design is sealed, okay? So it's going to hopefully impact some of their 2025 engine design. So the other aspect that I spoke about a little bit earlier was shot-to-shot variation. So no two shots, no two cycles of an engine are the same. And we tried to capture some of this from our simulations. So again, we got some needle measurements done at Advanced Photon Source. And what we found out was there was significant shot-to-shot variation from one injection to another injection. And that's simply because this is a cantilever, which has a natural frequency of oscillation. In an ideal world, that should be repeatable. But because the pressure is changing from cycle to cycle in the sac, in the orifice, we find that this off-axis motion is changing. So we imposed that in our calculation. And for the first time, we have seen this, that if you have shot number 1, for example, and shot number 2, you can clearly see the velocity patterns are very different inside the sac, inside the orifice. So this is telling us that this could be one of the reasons why we see shot-to-shot variation or cycle-to-cycle variation in an engine, because some of it is actually coming from what's happening inside the injector because of the shot-to-shot variation in the injector. Currently, each of these calculations take about a month on 256 processors. And you can imagine that we have to run maybe 20, 30 shots. Okay, so you can clearly see that this is very expensive. And in our new ALCC award, we are trying to see if we can optimize this further running on Mira. So the other advantage of having HPC resources is you don't have to take any shortcuts. So for example, when industry does these injector simulations, nozzle flow simulations, they typically try to do simulation on a single orifice. So say orifice number 1, 2, 3, whatever it is. That's because they have computational restraints. They do not have the computational resources. Now, when we do this 9-hole injector simulation, you can clearly see that sector simulations are essentially useless. Each of these orifices actually have different two-phase flow characteristics. The cavitation is different. The spray that's coming out is very different. And this is only possible because of the HPC resources that we have. And the other challenging question that Cummins posed to us was fuel dribble. So fuel dribble is a very applied issue. So what happens is during the fuel injection process, at the end of injection, during the main fuel injection, the fuel is injected, say, at 600 meters per second. So the fuel basically breaks up, ignites, combusts, blah, blah, blah. But when you look at towards the end of injection, the fuel that comes out at the end of injection has very low velocity. So it doesn't break up and it doesn't burn properly. So it results in hydrocarbon emissions. So Cummins basically came to us to see if we can develop a simulation approach to capture the amount of fuel that's being dribbled out from their injector. So their injector is 9-hole. We demonstrated this approach on a single hole. And you can see here that once the needle closes, this is static picture, so the needle is closed here. You can see this amount of fuel that's being dribbled out is what we are trying to get an estimate for. So obviously, if the sac is bigger, the amount of fuel that will be dribbled out would be less. If the sac is small, then the amount of fuel that will be dribbled out is less. Sac is big, there'll be more fuel dribble. So this is something that we told Cummins, and now we are trying to apply this approach on their 9-hole injector. It's a very, very expensive calculation, but again, you cannot do this with experiments. You cannot measure the amount of fuel that's being dribbled out from an experiment. And this is a real issue because unburned hydrocarbon increases if you have large sac volumes. So again, without simulations, it would be very difficult to solve this practical problem. So this is basically our workflow now. So we can go from nozzle flow simulations. This is actually a GM 1.9 liter diesel engine simulation. We can resolve the flow inside the sac and the orifice. We can understand plume to plume variation, and we can now understand how that affects combustion. So you can clearly see each of the spray plumes and each of the combustion regimes are a little bit different from plume to plume. Okay, and these simulations were not possible 3 years back. These are possible now because of some of the HPC and science developments that we have done. So I think in a lot of the fields, there is this question of RANS versus LES. RANS is some sort of a time average scheme, simplified turbulence model. And at least in industry, there's a lot of question as to if there is any merit in using large eddy simulations, LES. So we have been working for the last 5 years on trying to implement better and better LES models. And of course, they come at a cost. So this slide here actually has been used by all our industrial partners because the common question is, what's the benefit of using LES? LES is about 100 times more expensive than RANS. So there has to be a real benefit of using LES. So here we have done some work. We've taken experimental data from Sandia National Lab, looking at vapor penetration as a function of time. This is the fuel vapor that's coming out of your fuel injector. And what we observe is if we have a simplified turbulence model, as we refine the mesh size, we do get grid convergence, but grid converges to the wrong answer. It doesn't match the experimental data. With LES, we see that it not only grid converges to the right answer, but it also matches the experimental data. And that's because of the higher fidelity turbulence model. So with LES, we are actually able to resolve some of the large scale flow structures, and hence we are able to get the mixing better predicted. And hence we are able to get this vapor penetration better captured. So in industry, they basically use this slide to tell their managers that they need more computing power. Okay, so now we have started doing a lot of these combustion calculations. Again, a reason to say why we need LES. For example, LES is 100 times more expensive, like I said earlier. But if you look at RANS, a simplified turbulence model, with RANS, we see one spot of ignition, and that one spot of ignition tends to grow. With LES, we actually see multiple spots of ignition, which is what basically happens in a real engine. So we get better physics with LES, and that comes with 100 times more cost. Here, I have several slides, several things here to discuss, but the main key point here is that with RANS, when we do 2 different cycles, they give the exact same answer. With LES, when we do 2 different cycles, we get marginally different answer. And then the question is, how many realizations of LES are necessary to, for example, mimic experimental data? So we have started looking at these criteria like relevance index, and the idea is to understand how many realizations are necessary to mimic, say, an actual calculation, actual average of 16 realizations. So we find that if you want temperature to be correctly predicted by LES, we need 2 realizations. If you want mixture fraction, we need 5. If you want to get soot correct, we need 8. So this basically tells us that beyond 8 realizations, you really don't have much to gain if you run a 9th LES realization. But you really do not know this unless you run this 16 realizations and perform that average. Okay, last part of my talk is uncertainty analysis. So we have recently started looking into this. In the past, there has not been any reason to look into this because the simulations really were not that predictive. They were always being tuned. So, but still, the way to understand this, and I think most of you are familiar with uncertainty analysis, uncertainty quantification, is that if you have a simulation, you have multiple sources of uncertainties. So you can have uncertainty from the model constants, you can have uncertainty from boundary conditions, experimental data, fuel properties, model constants, chemistry, everything is a source of uncertainty, okay? In fact, nothing is certain, actually. So what we try to do here is, okay, we quantify these uncertainties. So we would talk to our experimentalist, we would talk to our fuels people, we'll talk to our chemistry people, and try to understand what are these uncertainties and how they influence these calculations. And we try to simulate, perform this sort of a workflow that I'll discuss again later. So this is a slide where we try to understand the chemistry uncertainty. Okay, so for example, this reaction mechanism is for biodiesel fuel, okay? And biodiesel fuel is used a lot, at least in many cases, 10 to 15% blend. And for a biodiesel fuel, our chemistry people say that these three reactions are most sensitive to ignition delay, okay? But they also tell me that these three reactions have huge uncertainty. So all these reactions have a factor of 5 uncertainty, okay? So if I just do a simple local sensitivity analysis where I perturb reaction rates of each of these reactions by a factor of 5, multiply or divide, this is what I get. So y-axis is ignition delay, x-axis is my perturbation factor, and you can clearly see the baseline is without perturbation, and this is a 2 crank angle difference. So if you look at the maximum, minimum, it's a 2 crank angle difference. And 2 crank angle is enough to misfire your engine, right? So with so much uncertainty, just from the chemistry, you can clearly see that your simulations could misfire, okay? So that's really not acceptable, right? So this is one way when we use global sensitivity analysis, we can actually improve the predictions. So we have an ALCC award with 60 million core hours where we are going to try and quantify uncertainties better and understand how they influence our target. So for example, in this ALCC award, we plan to run in the order of 10,000 simulations per day and understand the uncertainties from kinetic to non-kinetic parameters and how they influence our final target. So this is a sample result where we applied uncertainty analysis on everything apart from the chemistry, okay? So here, so the uncertainties are, for example, like I said earlier, model parameters, experimental parameters, etc. So this is a Caterpillar single cylinder engine, and for these baseline conditions, we match the experimental data very, very well, okay? And then we identify the uncertainty. For example, if you look at piston wall temperature, the baseline temperature is 553, and the minimum is 538, and 568 is the maximum. So then using a Monte Carlo fashion, we basically perturb all our parameters based on this uncertainty range. And for 30 parameters, using sparse techniques, we basically run about 100 simulations per speed load conditions. And this is some of the result that we can get. So for example, if you're interested in a parameter like engine out NOx, this basically tells us, this global sensitivity analysis, it tells us that parameters like Schmidt number and Prandtl number, which are basically modeling parameters, they affect the NOx results the most. So if we cannot actually match experimental data for NOx, it's basically telling us that this is the reason that we cannot match the experimental data. Similarly, if you're interested in soot, what we find out is the discharge coefficient of the nozzle and the angle of the nozzle is very important. So angle of the nozzle basically decides your spray plume, at what angle the spray plume is coming in, where it's hitting. So again, that becomes very important when you are trying to predict the soot. And yeah, so we have been able to apply GSA to understand some of this. And again, these calculations by itself are not very expensive, but when we launch them in an ensemble fashion, it really becomes capacity computing, and it starts to become very expensive. This is some work that we did with Chrysler. This project just finished, and this is actually what they call as a dual fuel combustion concept. So earlier I talked about gasoline compression ignition. Here I'm talking about dual fuel combustion. So we are injecting 2 fuels, okay? So what I'm plotting here is droplet radius and temperature, and this is basically the NOx. So this is basically a side-mounted gasoline injector. It's injecting gasoline fuel. The gasoline fuel basically evaporates and it's being compressed. Close to top dead center, we actually inject diesel fuel. We have a spark plug here, but the spark plug does not work. Okay, the spark plug is not activated. So the fuel is actually ignited because of compression ignition. At low speed, low load, we would actually operate the spark, but as we go higher in speed or load, we would stop operating the spark. We will try to ignite the fuel just based on compression ignition. Okay, so my task was actually to develop a CFD tool, and we were able to do this, but more importantly, we actually needed HPC to do some sort of optimization. So since it's a new combustion concept, they were afraid of trying it in an actual test cell. But in a simulation, you can do whatever you want, right? So we did some optimization, and we came up with certain conditions like EGR, ICL, DMP ratio, start of injection timing, which we thought was really optimum in terms of avoiding the NOx and soot island. So for example, if in a spark ignition engine, NOx is an issue. In a compression ignition engine, soot is an issue. So if we are able to marry these two concepts here, hopefully we were able to avoid some of these NOx soot islands, and you can see that based at least on our CFD results, our optimized results are able to avoid both the NOx and the soot islands. And again, in order to do some optimization like this, we had to do a lot of cases, and again, these were all run in an ensemble fashion. So HPC, we believe it's an enabler for simulation-based engine design. Of course, we are not there yet. It's going to take us maybe a lot more time. But anyway, with the resolution that we have and the science that we understand, we are actually able to do high spatial and temporal resolutions. We are starting to incorporate more and more robust turbulence models into our calculations. We have moved away from simplified chemistry, so we are able to incorporate more and more detailed combustion models, chemistry models. And in doing all this, we are able to solve one-of-a-kind problem. And for the industry, we are able to provide unprecedented insights. We are able to get some grid convergent results. With Cummins and Caterpillar, we have been able to modify some of the best practices in the industry, the way they operate their simulation workflow. And some of this work hopefully will enable us, because we are doing large calculations, we could also move our calculations into the next architectures like Theta and Aurora. So by doing all this, we have actually launched this program at Argonne. It's called Verify. It stands for Virtual Engine Research Institute and Fuels Initiative. It's basically a sort of a consulting service where the industry would come to us with a problem of their interest, and we'll try to provide them with a solution based on the expertise that I just described. So we have a lot of chemistry expertise. Of course, we have a lot of computing expertise. We have a lot of experimental data. And then we have people like me who know the domain very well, the science very well, who try to pull all this together. So this is the idea is to try and attract the industry to come and work closer with Argonne. I'm happy to take any questions.
So you mentioned that you used commercial software, Converge. So what kind of challenges you had scaling that, and like, did you have to tweak something, and how accessible was that to you?
So yeah, so when we first started, we were just adding UDFs, right? So that wasn't an issue. But slowly, when we started to do some real calculations, we needed source code access. So in the time frame about 2012, they started providing us source code access. So with 80-85% source code access, we have been able to do a lot. So we work very closely with Vitali, Marta, Kevin Harms, and we have been able to do a lot, actually. So not having the source code or not having enough of the source code has not restricted us yet. But I do envision that once we start getting into AMR, trying to scale with AMR, try to scale with embedding, I think that's when we would actually need the full source code access. But we are not at that point yet. And the key thing is industry is still way behind. So industry is still in the 100 processor, 60 processor range. So the existing algorithms actually work fine. So from a software vendor perspective, there is no real push from the industry to do this. So we are doing this because we are a national lab and we want to advance science. But from an industry, the push is low, I would say.
Could you elaborate on what talking you had to improve in the code, or
Sorry?
What did you have to improve in the code? What kind of?
So the way the code was written, I mean, it was, for example, it was serial I/O. So the first thing we did was MPI I/O, as simple as that, right? So a lot of the things that we have done is basically a low-hanging fruit. It's easy to do, it's not difficult to do. The complicated thing that we did was basically Janardhan and Convergent Science working together in trying to do this chemistry load balancing. So stiffness-based criteria, chemistry load balancing. We haven't seen that in literature. So I think that's a unique thing that we have been able to do. But the rest of the stuff is not very complicated. For a computer scientist, that is. For a mechanical engineer, it's quite complicated.
Could you say a bit more about your chemistry? Is it operator split from the transport, or is it how many species are you using? What's your time stepping integration scheme?
Yes. So it's operator splitting. Yes. And so we basically use this CVOD for chemistry, for integration.
I was wondering, DOE has a very, very high profile Exascale co-design project in combustion. I was wondering to what extent you have interactions with this Jackie Chan-led activity,
Yes.
whether there's been any lessons learned as a result of that, and
That's an excellent question. So we actually have a ongoing project with Jackie Chan's group, and so Jackie Chan focuses on doing DNS calculations of a flame. So it's basically a gas flame, co-flowing flame. She uses this S3D code. Her code is pretty much explicit and no two-phase flow and fixed mesh, right? So it helps us understand, it helps her and it helps the community to understand the basics of combustion. And that's what we are trying to do with her now. So she's doing these DNS calculations of combustion, and our idea is to basically data mine this DNS and develop what we call as a universal turbulent combustion model. So we really cannot afford DNS in our calculations, but the idea would be to data mine her DNS calculations and develop turbulent combustion models for RANS and LES. So this is a 3-year project. We are about halfway done. We have some nice ideas that we have currently implemented in this code Converge based on the DNS from Jackie.
It was not entirely clear to me on which terms do you collaborate with the industry, because it was not entirely clear that you do the work and they just benefit, or well, you benefit from the science and
Right.
they benefit from the money. Or
Oh, that's a good question. So I don't know if there has been a seminar here on how Argonne works with the industry, but that's a typical 1-hour seminar that the tech transfer people give at Argonne. I can be more specific on the way we work. So we have a couple of different projects, what we call as work for others. So the industry basically pays completely for our effort. So if they want 10% of my time and 50% of Janardhan's time, they'll pay for that. They'll pay for the computing resources, whether it's at LCRC or ALCF, they'll pay for that, and it completely cost recovery. So the Chrysler project was basically on that model because they wanted to keep everything proprietary. Then we have done some work with Cummins and Caterpillar. That's basically based on DOE funding. The mechanism is what we call as CRADA. So the DOE funds us. The industry either gives us direct money or they give us some in-kind support. And the industry can protect the information for 5 years. But after 5 years, we are allowed to publish everything. But at least the work with Caterpillar and Cummins, they have never stopped us. So they are interested in the science, and all the work that I have shown here, actually all the work that we have been able to publish. So there hasn't been any problem. So it has been a win-win situation till now, but we'll see how it is moving forward.
and what about the code? What happens to the code?
Yeah, so the code is, Converge is very careful, right? So they do not want any proprietary stuff going into their code because it complicates things. So So basically, because the industry is interested, so they would work with us, we would develop a model, and usually that tends to become part of their next round of commercial release.
So I had a related question, Sibendu. On one of your slides, I think I saw Combustion Institute. So is that something that many of the companies belong to? And
right. So the Combustion Institute is basically not only industry; it's mainly academia. So it's led by the academia. National labs play a role. Industry plays a role. Industry's role is funding the seminars and workshops usually. But yeah, it's basically academia driven.
So yeah, what I was wondering is whether that would be a forum at which you could present your results and therefore motivate more of industry to take this approach.
Right. So we present extensively in the Combustion Institute. The last meeting was in May. I think we had 5 papers. In general, national labs present a lot in the Combustion Institute. I think it's a very good forum for our postdocs and scientists to talk about their research. It's also a very good forum to get students, good students.
Another question?
You mentioned that you achieve the load balance based on actual load. How do you do that?
That's a question for Janardhan.
Well, basically, so how the load balancing was done is you try to divide the mesh and give equal number of cells to every processor. But what happens is that some cells don't have much computation going on in them. So what we do is we calculate the amount of time spent in computation the previous time step and use that as a weighting factor associated with every computational cell. So for example, one processor may get 10 cells in the next time step and the other may get 100. But their overall computational load might be quite balanced based on an estimate from the previous time step. Again, the reasoning is that the load does not change too much from one time step to the next. It is changing over the whole simulation, but that gives us a good estimate and really improves the load balance. So we don't have any bottlenecks where you just have one processor that's stuck near with all the cells near the spark plug where a lot of stuff is happening, ignition's happening. That's all the other 1,000 processors are just done with their work. So yeah, that's how we do it.
Thank you. And another question, how do you capture the interface between the droplet and the gas?
That's a very good question. So we basically use WOF, so volume of fluid type of techniques. So when we do the nozzle flow and spray calculations, we use WOF, and then we basically transition to what we call as a Lagrangian Eulerian approach. So we basically track the droplets. So when we are able to resolve the interface, we use WOF, and then we basically transition into a more ad hoc approach of Eulerian Lagrangian, which is pretty standard.
Thank you.
You're welcome.
You mentioned that you use the matches to do the load balance. And since the mesh is changing at every time step, so do you need to call Mattis at every time step?
That's a good question. So we call Mattis, so that's a user input, and that's something that we tend to optimize. And that forms part of our best practices for a given problem. So typically we would call Mattis maybe every 50 time steps. In some cases, maybe 25 time steps, maybe 100 time steps. So that forms a part of our optimization study when we get a new engine or when we start working with the new hardware.
Then after each time you call Mattis, are there many data movements between the last time step and the one after the?
Yeah, so the cost of doing a load balance with Mattis is about equivalent to the cost of doing a calculation over one cycle, one time step. So, so Mattis comes with its own overhead, but it's not too much. So if we load balance every 25 time steps, every 50 time steps, it's not too much.
One more in the back.
So what kind of subgrid scale models do you use?
Yeah, so for turbulence, we tend to use, for large eddy simulations, we tend to use dynamic structure. We have looked at Smagronsky type of models. But we like dynamic structure model. For turbulence chemistry interaction, subgrid scale models that we typically use are, for example, RIF, flamelet-based models, if you're aware of them. We have a bunch of models, but these are some of the more known models that we use. If you're more interested, we can talk more, actually.